right? That's kind of the latest thing you guys got to in your material research, right? Does that make sense?
Yeah, yeah.
Like, to me, this is a computational filtration system. That's what you guys have designed, right? Material comes in and it comes out in a different way, right? Or maybe it doesn't come out at all. In your world, this material is water. This stuff, we haven't decided what it is, right? You started it from a water logic, right? And what temperature means to this world can change, right? Like, you can say it's temperature, you can say it's flow rate, right? It's just a parameter that controls flow rate. So if you'll know by now, if you have a high temperature, you have more porosity. If you have a low temperature, you have less porosity. So you can just, this is a flow rate parameter. So this is the concept of what I was telling you last semester, right? What you have is a metamaterial system that is highly flexible, right? And how you apply it to your central research, in a way, it doesn't care. That's our intelligence as designers, right? You're designing a base computational machine, and how we use it is what we do as designers. So what I'm hearing from you now is, look, there's a material that comes into the system and affects it, right? And there's a performance level the system has to apply to that material. You haven't defined what that is, right? That could be energy harvesting, which means you want to maximize turbulence in the system, because when you create turbulence in a collection mechanism, that's how you create energy. Do you understand what I mean?
Yeah.
Okay. Right? In a wind turbine, how you get energy is you get the wind to flow across this and it turns. That's how it creates energy, right? So in your world, it could be about creating a very fast flow in the system, or it could be about making a very slow flow to increase the amount of energy collected. But that's a very simple problem to design, right? It's like, can you design this filter, this computational Brita filter, basically, which allows water to pass through it very quickly, or it allows water to pass through it very slowly. And sometimes it does it both in the same thing, depending on your design, right? So it starts to guide the water. And that's what your computational system will start to do, right? It will have this feedback loop between how it's distributing material and how the secondary material passes through it, right? So how does the filter material interact with the water material? And I think you guys have already, the word temperature is what you guys are stuck on, right? But the idea of a parameter inside the system that decides the kind of geometries that result in the system, that's a very clear idea, right? Like, that's just a parametric system. Is it, whether it's temperature or something else? The only thing you've added right now, which I think is a great step, is this concept of the secondary material that has to interact with your filter, right? And Daphne, what you were talking about is how you make this not 2D, I think is also very easy. Your system actually, one of its advantages is it doesn't care if it's 2D or 3D. The logic works the same, right? Like if you start with a cube full of particles and then you run your simulation, you get a 3D filter. So it's very similar to the other team in the sense that I think you guys have a very clear set of steps. I think you have 2 steps to do right now. Step 1 is you generate a series of outputs of your filter at different information parameters, right? Let's call it temperature for now. We can change it later, right? So we have to test the assumption that temperature produces different results in your system, right? And I think that's pretty much given, but we have to prove that. I didn't see that catalog from you guys yet. Do you agree?
Yeah.
Computational renders. We didn't see that yet, right? It wasn't very clear. The second thing is you take this catalog and you treat it as your kind of water filtration system in Maya, right? You just export that geometry, right? And then step 3 is we have to start to understand this feedback loop between water flow and result and living geometry, because that's what I think is interesting about your project. Is this is not a set thing, this is living. It's a computational machine, which means it can respond to real-time information from the site, right? And the third thing we'll need to decide is, what is the relationship between these two? As in, are you trying to harvest energy? So what does harvesting energy means? Or are you trying to dissipate flow? What is the goal here? You see what I mean?
Like initially, like our goal is like distribute this material, which is water, and distribute.
What does distribute mean? Right? Distribute can mean, like, we're talking very literally. Water comes in a central source and it goes out in 100 different directions. That's distribute, right?
Yeah.
Another way to think of it is if you're harvesting it, you want it to come out in a very concentrated, designed way. Or the other thing to say is you want to convert it all into energy. So it's coming in at 50 millimeters per second of speed and it comes out at 5 because you've harvested most of that kinetic energy, right? So we can do all of this computationally. The question is, what are we trying to do? And how does your machine design itself to maximize the result, right? And then how this becomes more tectonic is the question of what is this machine tectonically, right? Is that material you are shaping on site, or is it a living material that can reorganize itself, right?
Okay.
I think those are your two decisions. There's not a third, right? Is it some sort of actuatable living material, or is it a machine that gets controlled using external stimulation? So is it a bit more of a site-based thing where other agents form it? You see what I mean?
Mm.
That's, to me, the decision you guys have to take. And I don't think we have enough information yet to tell what it's going to be. So we have to play the design game, right?
Yeah.
So I think there's two areas of research immediately. One is we need to be pushing this purple stuff forward. I think you guys did a great job over the break with what I saw there. And the next steps, from my understanding, are pretty clear. Like, can you catalog it? Can you show us the effect of temperature, even if it's the same temperature in the entire population? What does it produce at a high population? How, if you start to do dumb things like saying, okay, half the population is one temperature, the other half is another temperature, can you show that difference in the same thing? Then the next step will be using these bitmaps. Can you start to differentiate the temperature? Then the fourth step will be, does temperature become a living parameter, if you know what I mean, right?
Mm.
Let's take that step by step. The next area of research is running this as a filter, right, in Maya, right? Running the water particles through it. And the final thing, which I thought was amazing that you guys have done, is the viscosity studies, right? And the question is, what is this viscosity study about, right? So one way to say it is like, if this is on-site water, your viscosity studies don't mean anything there, right? But the other way to think of it is the viscosity study has something to do with your filter, right? Because right now you're saying your metamaterial is all the same material. It's just differentiated by its temperature behavior. But I think, and this is what we talked about last term, is also with the fire team. If you start to have a heterogeneous material rather than a single material, all that means is that study you showed, Daphne, which is multiple viscosities. That's all a fluid, but one is oil, one is water, and one is honey, right? But you break down that differentiation to such a point that you produce a third material. When you look at the end result of some of those simulations, you can't say that's three things together. You're saying that's one new thing, right? And the question is, what is that one new thing? In my mind, it's this. It's that computational machine of heterogenic materials. Again, is that really material, or is that different types of robots? It doesn't really matter right now, but the potential is clear. You're producing different types of agents inside each other, inside the same material system, or the same, let's call it filter system, that can provide very different results that relate to the quality of filtration or energy harvesting you're going to be doing. Right? That's why I think that viscosity research is great. We can just convert it into agent population properties, right? All that you showed there is viscosity. Viscosity is the level of attraction and, you know, bounciness off of other particles, right? So it's kind of, I think it might seem like you guys have gone in very different directions. I actually don't think so. I think it all comes back under this concept of a heterogenic computational filter, right?
So you think that it is worth exploring, like a new material that can collect and filter and distribute at the same time? It doesn't have to be one material.
Not a new material, which is composed of.
Yeah. So the question is this a material? Like I'm saying, is that a material, or is that like I said, is it a simulation property? And then something puts it down. I think that will be the most disappointing, right? Is it literally you're designing a kind of material that can be deployed in site? That's an option. Or is it a kind of smart particle that has an ability to move and it's using this as its brain, right? That's another option. You see what I mean? That's a blanket statement, right? It depends on the project. I'm not saying you're going to do that. I'm saying those are the options, and we need to, I think, keep our minds open to see what the potential is, right? Because if it's just about site-based material, it has amazing benefits, but also has big downsides, right? Like, you have to ask a serious question, like, okay, what is this viscosity study about? And, you know, so that's why I'm saying right now there's a lot of potential in your project. I don't think it makes sense to kill it. I think let's push a bit forward and see how let the catalogs speak for themselves before we make these decisions without information. So,
so I guess our next step is actually like cataloging, for example, the temperature influence.
Yeah.
Like make it more evident.
I think immediate steps for Wednesday, the 3 different catalogs of the different information parameter, if you don't want to call it temperature because it's confusing, and then running the water filters through it, right? If you have time by Wednesday to also get the multi-temperature system working or the multi-information system, great. But first step, definitely clear catalog, same population, different information parameter, run the liquids through it. Find a way to measure the liquid flow, right? I think we could do that. It could be this, in Maya, color the particles depending on speed, right? For example. So we can see how fast it's coming in and how fast it comes out, right? All that kind of stuff. And I think you guys really need to get better at documentation, which is like, right now, everything is green, right? In your catalogs, show different colors to show the different information. Because eventually when you mix it, that will become really important. But I think you've made great steps. I think it's also very clear. Like all that stuff you guys talked about, in my mind, just gives you more purpose. It doesn't really change the direction too much. I think it clarifies your purpose. And the decisions, how to turn this to tectonics, to me, are also very clear, right? You know, I think for this term, it's highly likely that we'd be deploying some site-based infrastructure right now. I think that's how we should start to think of it, right? It's, you know, you can imagine whether it's in a semi-arid environment, like you said, Daphne, so it's dealing more with rain, right? And that's not a trivial decision because your system will have to deal with water flow that is Z-based, right? Versus if you deploy it in another system, which is based on a river flow, which is a very different problem because it's multi-dimensional XY flow, right? So the quality of water flow is very different. And the answer could be very different, right? If it's rainflow, it could be about harvesting and storage. If it's about river, it could be about redistribution, right? Like, is this a different kind of dam, right? Instead of just blocking water, it spreads water intelligently. You can start to see how this can become a tectonic problem very, very easily. Versus if it's a water storage system. And to be honest, why can't it be both, right? That's the whole point of computational systems. You just change the parameter locally and the system adapts. In one area, it's harvesting vertical water flow. In another area, it's distributing linear water flows. And all that changes, it's the same system. All that changes is the parameter and the information in the system, right?
Yeah.
And when it's not raining in summer, the system redesigns itself to do something else than in the wet seasons, which are doing something else. Again, this is the advantage of it being a living system rather than a stable, static thing. You see what I mean? And that's why I think it's really exciting.
Theo's feedback was like, go back to phase change and
this
like,
is the phase change. You need the temperature stuff to do the phase change, right?
Yeah, because also different. It's different temperature, but not different. You don't have to go to ice to be a phase change.
But what's interesting in the work you've done recently is your systems are more stable, right? Like the other team, you now have these like stalactite things, right? And I think what you need to show, because Theo's like, he has a point, like, for example, as you move to the more colder temperatures, I think you can dictate the relationships between particles more, right? So right now you're very loose, it's just based on attraction, but like you can start to be dictating, which is when they come really close and it's very cold, they have to snap into certain positions around each other, right?
How to do that? We couldn't find a way to do
Huh?
We have to add a code, a line in the code to do that.
Yeah, so there's something extra that should be added, like crystallization.
Yeah, you would have to have like a function which snaps the particles next to each other.
And it becomes temperature equals like minus something, do this.
And because then you'll start to get very clear, like crystalline formations versus some of these more fluid ones. And if you think about the difference, the fluid ones will allow water to flow smoothly. The crystalline ones will create turbulence, right? So again, all of this has reasons. So yeah, I really think there's a lot of clarity. We can get to that step next as well, which is once you do these catalogs, we can start to push the phase change forward. So there's actual different phases, right? Like I think what you've done looks really good for like a liquid phase, right? You can start to see if you start to snap the geometry more, you'll get more crystalline relationships, right? And how you do that is you take a particle and you force it to have the same X and Y value as its neighbor particle. For example, you can be really dumb about it.
Mm-hmm.
You know what I mean?
Okay. And if we have like a question in code, can we like send you a line of the code and like?
Yeah, me and Octavian are still around, so of course.
Okay.
It's been a very slow process, this developing. I don't know.
I don't think it's slow. I think you guys are just like, and it's good. Like, I don't think you should stop being unambitious. Like, be very ambitious, but don't beat yourselves up. It's not slow. You guys have done a great job. You've learned a whole new language and are doing great results in 8 weeks, for fuck's sake. Like, honestly, I'm sorry. Like, anyone who tells you that's slow, shut the fuck up. Like, like really, this takes months. Otherwise, I think you guys are doing a great job. I think you should be ambitious.
Yeah.
Keep pushing, but you've done a great job. Like the question now is, let's keep being ambitious. I think you're getting good results. I think at the end of the term, we can have some really interesting stuff.
Hopefully.
Just, you guys really need to get better at cataloging.
Oh yeah.
Put some effort into that, right? Make the diagrams clear. You know, that it'll really pay off in the next few weeks.
Yeah, there's a question now that basically we were thinking to move on to some physical experiments for this week and to also print some stuff.
Yeah, sure.
Yeah, any suggestions, and from what we saw, like which would be.
Yeah, I think the stuff you have is printable, right? Especially if it's deeper. I think you could do really interesting results, right? Like if you take a 3D print and get a cube of water with food coloring in it, and you push that thing through it, you can see how the water, and you take a slow motion video, you can see how the liquid will move through the materials and stuff like that, right?
Okay. We also got hydrogels, like we have the spherical hydrogels, and we were wondering if hydrogels can be printed. Like, has anyone done it? They can be printed.
Yeah, but we don't know in DPL.
In the or like, yeah. Okay.
Yeah, in terms of 3D printing, that's the stuff I can think of, right? But also Apple might have good ideas in this, but like use like water and food coloring, and you can watch how especially if you can print in a porous material, and instead of pushing it down, you can let the water get sucked up into the material. You can see how the water will move through the material if you use food coloring, which could be a really interesting study.
So yes, we were thinking that we need to print something that interacts with water, not to print something that is static.
Yeah, that's what I mean. Interacts with water, that's harder. That's
hydrogel, and like it interacts with water by just expanding like its shape. But
Yeah.
like
The thing I can think of is like print the negative and cast the hydrogel.
hydrogel, yeah. Okay.
You know what I mean?
Yeah.
Yeah.
Okay.
And then
Like maybe like something.
it'd be very hard to take out the hydrogel, but again, you can put it in a cube of water and see how the water erodes the hydrogel over time. Stuff like that could be interesting. But yeah, again, if you can, great. If you can't, I'm not too fussed. But talk to Apple; he'll have better ideas. I think your computational route in relation to the main concept to me is very clear.
Okay.
All right.
Yeah.
Okay. Thank you, Mustafa.
Send me some stuff on Wednesday, please.
All right. So we don't have anything tomorrow?
Tomorrow.
Tomorrow's Tuesday.
Tomorrow's Tuesday.
Yeah, Theo mentioned some.
Not that I know of. I'll ping Theo. Yeah. Pause for a second.
Yeah, we froze.
Okay.
Okay, maybe.
What were you saying?
Okay. Can you hear us now? Okay. Thank you.
Thank you, Mustafa. Thank you.
See you.